Hello everyone. I hope you are fine and doing well. So today our lecture is about cryptographic properties of Boolean functions. So it is today lecture is about the cryptographic properties, which is the continuation of my previous lecture. I hope this lecture will be quite good for you. So let me start with first definition that linear Boolean functions, a Boolean function which can be represented by this expression like this one, we call it as a linear Boolean function. And negation of or complement of a Boolean function is represented by this expression. So G bar is G XOR 1. So this will represent negation or complementation of a Boolean function. So affine Boolean function, the set of affine Boolean function can be represented by this expression A of alpha, and this is, you know what, alpha is the constant of this linear combination, and C is the addition of a linear function. In linear function, if we add C, then this linear function become affine Boolean function. So, dear student, corresponding to every Boolean function, we associate a characteristics form or a sine function. This is, we call it as a sine function. And by the way, we are using this sine function just because of the fact that this will be quite helpful while calculating a Wash-Hedammer transform and while calculating the non-linearity of any Boolean function. Say I have one function, let me give you the example. It is one of the function like z2. So it take two input 0, 1, 1, 0 and 1, 1. These are just inputs, and the f is basically the is correspond like output 0, 1, 1 and 0. I take as this function as a what you call the XOR of these two element x, and this is, I call it x, this is y. So I call it as a just XORing both the input. So I get 0, 1, 1, 1. So the complement function or sine function of these are minus power 0, I will get 1. So minus 1 to the power f to the power f. So the here I get sorry, minus 1. So minus 1 to the power 1. This output of this function, it will be the power of this minus 1 to the power f. I will get minus 1, then minus 1 to the power 0, last one, I will get 1. So in that case, if you can see this one, the f hat will be 1, minus 1 and 1. So these are just this. You can write it like this one, like this expression. So Hamming weight of a Boolean function is number of 1 in truth table. If I call it as a function 0, 0, 0, 1, 1, 0 and 1, 1. I take single valued Boolean function just as to understand these are just inputs and this map on single value. I take it x and y and x XOR y. So this is my x, this is my y. This whole what you call the column is x and this whole column is y. So I XORing both inputs 0, then 1, 0, XOR 1 is 1, then 1 XOR 0 is again 1, then 1 XOR 1 is 0. So 0 XOR 0 is 0. So if you can see the Hamming, like Hamming weight of f in this case will be 2 because number of 1 in any Boolean function is Hamming weight. So number of ones are 2. So Hamming weight of this function f is 2. So another Hamming distance, and you know what? Distance is always among between two functions, two or more than two functions. So distance of these two functions, like if I take x and y, this is 0, 0, 0, 1, 1, 0, and 1, 1. Sorry, this is 1 and 1. So this is my f. This is 0, 1, 1, 1. So I take another g, which is 0, 1, 0, 1. So how many places are there in which f and g are differ? That is 0 and 0 same, 1, 1 same, 1, 0. They are differing over here on this part, on this output. 1, 1, these are same. So the difference, Hamming distance between f and g are 1. So another, the support of a function is number of input in which function give the output as a 1. If I say I have a function which is 0, 0, 0, 1, 1, 0, and then 1, 1, and I take function as a function f from z2 to z2, and in that case if I take 1, 0, 0, 1, so how many places on which the function give me the support of this function is f is f of x, for which the output is 1. So how many places are there? This one and this one. So support will be 2. So if you can see the balancedness, so number of what you call a Boolean function is said to be balanced if number of 1 and zeros are equal. If I say I have two single valued Boolean function which take two input, that is f 0, 1, 1, 0. So in that case, if you can see the output, number of zeros 2, number of ones are again 2. So the probability of 0 is 1 over 2, and the probability of 1 is again 1 over 2. In that case, the number of zeros and number of ones in this function, if you can see over here, is same. In that case, the function f, which is single valued Boolean function, is balanced. So the number of variable in the highest monomial with the zero coefficient is called algebraic degree. If you can see this, if I take function x1, x2, so if I can take x1 XOR with x2, so the degree of f in this case will be 1. If I take another function x1, x2, in this case if I can take x1 and if I can say g is x1, x2, and x3. If I take x1 XOR with x2 and x3, so in that case degree of g will be 2, because the product term over here is 2. So the maximum uh, highest order monomial here is 2. So degree of g is 2. So basically I'm writing this as a and f algebraic normal form of any function g. So degree, algebraic degree is closely related with algebraic normal form. So these are just Boolean functions, and these Boolean functions through which we can categorize with respect to degree of a Boolean function. So if you can see the imbalance of a Boolean function, that is number of element from this what you call the domain for which the function is 0 minus number of element for which the what you call it function give you the output as a 1 divided by 2. It is called the imbalance. If I say if I have input 0 0 0 1 1 0 and 1 1, so my function is 0 1 0 0. So how many places are there that for which the output is 0? So I have three places. 3 minus how many values in domain for which the function gave me 1. So there is only one output for, there is only one a that is belonging from this domain which give me element 1. So I, in that case it will be 1. So the imbalance of this will be 1. So if I say if this is another function, like I take another single valued boolean function that take two output and map on one output, like 0 1 1 0. So in that case imbalance of f is 1, but imbalance of g is, if you can see, 1 over 2. Since this function is balanced, in that case number of zeros will be 2 minus 2, so it will give you the 0. So this claim that the balance function, the imbalance is always 0. And I can say a function which is balanced is imbalance will always be 0. So this is another definition of that is based on Hamming distance, how to calculate the correlation between two Boolean functions. And this is quite easy. If you can look over here, and this is 0 0 0 1 1 0 and 1 1. So if I take f, this is 0 1 0 1, and I take g as 1. So in that case, if you can see over here, the Hamming distance between f and g is the number of places where both output are differ. In one place these are same, this is second place, so Hamming distance will be 2. So here n is 2. So in this case, f and g, that is 1 minus 2 divided by 2 power 2 minus 1, and this is 1 minus 2 divided by what it would be. So what it would be 2. So in that case, if you can look over here, the correlation between f and g are 0. So they are not correlated. F and G are not correlated. So I just put algebraic degree. I have discussed it already. So fixed point of any Boolean function f is said to be a fixed if f of p equal to p. A point P is said to be an opposite fixed point of a Boolean function, multi-valued Boolean function f, if f of P is equal to its complement. So if I take this Boolean function, that is 0 1 2 as a input, and its binary form is 0 0 0 1 1 0 and 1 1. I take this as a output of this Boolean function is 1 3 2 0. If you can see this, it is binary 0 1 1 1 1 0 and 0 0. If you can see over here, the 2 is mapped on 2 under f. That is uh, under this transformation, if I can say 0 1 0 1, if this will be 0 1, then 1 1, then again if you can see 1 0 is map on 1 0, and then 1 1 is map on 0 0. If you can look over here, this one and this one. That is, if you can take 1 0, it will give you again 1 0. So this will be a fixed point. So in that case, 2 is fixed under f in this function f. So this is 2 is the fixed point of this Boolean function, multi-valued Boolean, that take two input and map on two output. So another definition is contractive or opposite fixed point. If I take 0 is map on 1 under f, and 1 is map on 2 under f, and 2 is map on uh, 3 under f, and 3 is map on f on 0 under f. In that case, if you can see over this element 0 1, so 0 1, if you can take the output is 1 0, and if you can take the complement of this one, that is complement of this one will be 1 0. So this is, you know what, the opposite fixed point, that is, this is opposite fixed point, that is 1 0 1 give you 1 0 under transformation f. So any Boolean function without fixed point and opposite fixed point is better against differential attack as compared to those having fixed and opposite fixed point. So these are some of the cryptographic properties of a good Boolean function. So let us take some other examples, like how to calculate its what you call the other Boolean cryptographic Boolean properties. The next very important definition is nonlinearity of Boolean function. So the nonlinearity of Boolean function is very important with respect to cryptography. So what it say? It say that the distance of f any Boolean function from all of the affine function, that is minimum of Hamming distance of f with all a, that is alpha is the set of all affine functions in the space of Boolean function b n. So the higher nonlinearity is one of the essential criteria for designing a good crypto system. So let us take one example, and and in order to understand the basic meaning of the nonlinearity and how one can calculate the nonlinearity of any Boolean functions. Like if I take one function like f2, this is from z2 to z2, this is one of the single valued function, that is I take two input and map on single output. So this will be input, that is x and y. This is function. I can write it in term of a row, and it is here I can write it like column. So you know what, these are all affine function which we have talked about in previous lecture. So I just take this here, it must be f2. So I take the Hamming distance of f2 from all these affine functions. That is Hamming distance between f2 and f8 is like how many places where f2 and f3 are different. That this is one place, this is 0 and this is 1. Count it as 1. This is 0 and this is 1. Then 2. This is 0 and this is again 0. So there will be no counting. So this is again 1 and this is again 1. So in that case, here we can see this one. So the here if I can say 0 1, then 0 1, so the 0, so there will be 2. So if I can say count it Hamming distance between f2 and f9, so here there is a difference Yes, count it 1. So there is no zeros over here. This again 0. So there is no counting. So this is 0. This is 1 counted. This is 1 and this is so Hamming distance is 3. Similarly, this Hamming distance between f2 and f11 is 1. So Hamming distance between f2 and f16 is again 3. So in that case, if you can see the definition, that minimum of Hamming distance of f, uh, that is f2, and from of all affine functions, so it will be a, if I can take this, so I have to take the distance between f2 and f8 is 2, and the Hamming distance between f2 and f9 is 3. So Hamming distance of f2 and f11 is 1, and Hamming distance of f2 and f16 is 3. So in that case, the minimum of all these are 1. So in that case, we can say the nonlinearity of Boolean function is 1. So this is one of the mechanisms to calculate the nonlinearity by using a minimum of Hamming distance. So there are other criteria which through which we can calculate the non-linearities of Boolean function. Likewise, by using Wash transformation. So by definition, let x be any vector and w is another vector which is belonging from binary n vector space. So we can take dot product of these, and we will get this one. So this is, you know what, the linearity between x, w and x. So this is again belong from Z2. The Wash transformation of Boolean function on uh, binary vector space is defined over here, this one. So the inverse transformation of this is defined over here. If I can say this is equation 1 and this is equation 2, so this is inverse Wash spectrum. So how to understand these kind of what you call the definition. So in order to understand all these, so we need to do some what you call the uh, to understand this definition, we take one example. So I have one example like how to calculate Wash spectrum of the Boolean function f2 from z2 to z2, and I take f2 as this one, x1 and x2. I take it just f. You don't mix it with f2 with previous example. So I take f2, that take two input and map on one output. That is x1 and not of x2. So by calculating this, we have, if you can see, this is x1, x2. This is my f, which is x1 and negation of x2. This is 0. This is again 0. This is 1, and this is again 0. So I take w vector, which is belonging from z to 2. So I take this as a w, this vector as a whole, that is this one. I take these as a I take this as just Z22. So I take this, and this is my X, like this one is. This is capital X. So if I can take capital X is 0, 0, and this is 0, 1, then 1, 0, and then 1, 1. So this is my X. So I just, this is the dot product. I just take W, this one, like vector, that is 0, 0, then what you call it as a 1, 0, then 0, 1, and then 1, 1. So how to calculate this one? So I have to take the dot product of this element with this one. So I take 0, 0, the dot product of 0, 0. So what I will get, 0 into 0, then corresponding what you call the dot product of corresponding what you call the 0 0. So in that case you will get 0. So similarly, if you can multiply all these, we will get 0. If I can take this one element like this one, so I have to multiply this first this one, like if you can see this one, how this I get this one. So this one is like this, and my W is like this. So W dot X, that is W is 0 1, and its dot product with 0 comma 1. So in that case, if you can see, this is a two tuple, this is again two tuple. So the in dot product, the corresponding element are multiplied 0, then 0, then I take this just a dot product, so 0, then 1 with 1. So this is 1. So I get this. So if you can see, I just take dot product, and this is, you know what, W is W1, W2, and X is every time X1 and X2. If you can see, dot product among these are W1 X1 XOR with W2 X2. So if I can take this one like this one, the first entry is this one, and I just take this element like first element 0 0. So how many W's are there? Are what you call one W, you have to multiply it with every X. So 0 uh, into what you call it as a 1 0. So how you will 0 into 1 plus 0 into 0, you will get 0. So how I can get this? If you can see this one like this one. So if you can see this one, how I can get this is 1 0 and dot product with 1 0. So this is multiplied with this one, I will get this, and if I multiply this with this, I get 0, so I get 1. So similarly, if you can take this one and this one, this is W is 1 0, and second one 1 1. In that case, if you can look over here, this is my x1 and this is x2. This is my w1 and this is w2. So w1 x1 XOR with w2 x2. If you can see this one, so you will get 1 XOR with 0. So you will ultimately get 1, this one. Similarly, if you can see this one, in that case, W is 0, 1, and the X is this one, like 0, 0. In that case, if you can multiply 0 into 0 XOR with 1 into 0, so you will get 0, this one. So how I can get this? So I just take again W as a 0, 1, and X as a this one, this element. 0 1. In that case, if I can multiply 0 times 0 plus XOR with 1 times 1. So from here I 0 XOR with 1, you will get 1, this one. So similarly, I calculate for all these elements. So I calculate W XOR W times X. So F XOR with W into X. So I just take XOR of these elements with this function. So I just XOR it. 0 XOR 0, 0 XOR 1. So 1 XOR 0 is 1. So 0 XOR 0, you will get this. So similarly, I XOR F with every element. So you know what are these? These elements are basically W times X. Okay. So I just XOR this with, so I will get, these are basically f f of x XOR w into x. So I just take power of minus 1 to the power f XOR w times x. So minus 1 times 0. So minus 1 times 0, you will get 1. So another one, minus 1 times 0, you will get 1. So minus 1 times 1, you will get minus 1. So minus 1 times 0, you will get 1. Similarly, all of you have to calculate like this. So you take this as an input, minus 1 to the power this output of f of x or w times x. So if you can take 0, so you will get 1. So this 0 is to the power of minus 1 to the power 0. So if you can add these 3 minus 1 2, so in a column wise you have to add these all. So in that case, dear student, you will get wash spectrum. And this is, you know what, f of w, this is wash spectrum, which is 2 2 minus 2 and 2. So this is a wash spectrum. So the inverse of the wash spectrum is like this one, the minus 1 to the power f of x equal to 1 over 2 power 1 over 2 power 2, and this wash spectrum into minus 1 to the power w time w into x. So we have wash spectrum. So I have wash spectrum. So what I have to do is to uh, take w, which is this one, 0 0 0 1, sorry, 1 0 and 0 1 and then 1 1. So I take this as a vector w. So I just take minus 1 to the power w times x. So w times x is what? So if you can see this one, w times x, this is the input of w times x. So if you can see this one, so this is minus 1 times w time. So minus 1 times 0 is 1. So if you can see these are 0, so I take this minus 1 to the power 0, minus 1 to the power 0, then minus 1 to the power 0. I just take all this 1. So the another one, this minus 1 to the power 0, minus 1 to the power 0, then 1 to the power minus 1 to the power 1, minus 1 to the power 1. So in that case, I get minus 1 minus 1. In that case, if you can see this one, this is my was, if you can see this one. So these are just and my was spectrums are like 2, 2, minus 2, and 2 from previous example. Here you can see I just take these from my previous example. So what I have to do is to calculate this part of my definition like this one. I just multiply was spectrum which I have calculated with my previous example like this one, multiply it with these element, that is the output of this one, this one. So I just multiply this with minus 1 to the power f. So I have to multiply this with 2 2 2, then 2 2 2 this with this one. So then I have to multiply this with this one, as a row wise I have to multiply it with every element. So what does it mean? So each and every element is multiplied by its corresponding spectrum value. This is multiplied with, the whole column is multiplied with 2, this whole column is multiplied with minus 2, this whole column is multiplied with 2, and this whole is multiplied with 2. So in that case, if you can see this one, so I get this one. So I have to sum apply the sum as a row wise. So what I have get 6 minus 2, which is 4. In that case, row wise I just calculated, add all of the element. So I get 4 4 minus 4 and 4. So this is 1 or 2 the 2 to the power n. So in that case, our Boolean function is, does it n is 2, because f is from z2 to z2. So here our n is 2. In this case, 1 over 2 to the power 2, which is 4, 1 over 4. I have to divide this with 4. So I will get 1, 1 minus 1 and 1. So what does it mean? 1 means 0. 1 means again 0, minus 1 means 1, and this is like this one. If you can say this one, f of x. So if I just will take if you realize this function like I have told you about sine function, which is this one, minus 1 to the power f of x. If you have sine function, then this is, you know what, this is the sine function, and you have to tell the original function in Boolean variable 0 and 1. So what does it means? If I say is f of x output is 0, then f hat output will be 1. And if f of x output is 1, so uh, like f of x output is 0, f of x output is 1. So in that case, the hat value will be uh, like 1, and for hat value for 1 is minus 1. So here I have hat values, so I have to take Boolean variable. So minus 1 correspond to 1 and 1 correspond to 0. So if you remember, f of x is minus 1 to the power f of x sine function. So I just get 1 is correspond to 0, 1 is again correspond to 0, minus 1 is correspond to minus 1, 1 is minus 1 is correspond to 1, and 1 is correspond to 0. So if you can see this, this is my original function to which I have to calculate this for spectrum. So if you know the relation between nonlinearity and Gauss spectrum, then you can easily calculate the nonlinearity in another way. This is another formula to calculate the nonlinearity by using Gauss spectrum. If you could put Gauss absolute of Gauss spectrum and take its maximum and put over here, so you can easily get the nonlinearity of that Boolean function f. And from previous example, the maximum of Gauss spectrum, if you can see the absolute, take its absolute, make all these values from negative to positive, and then take its maximum. So maximum will be 2. So in that case, the Gauss spectrum, maximum absolute values of Gauss spectrum is 2. I just put it over here because n is 2. So I put n over here. So I get nonlinearity of this Boolean function is 1. I hope this will be a quite good method to find the non-linearity of Boolean function. Another thing which will also be utilized to calculate the Gauss spectrum is Hadamard matrices. If you can see this one, the Hadamard matrices H of order n is n by n matrix of ones and minus 1, in which H into H transpose equal to n times identity matrix of order n. Let us consider H1 is 1, H2 is like this matrix, and H4 is 4 by 4 matrix of the form this one. If you can place H2 over here, H2 over there with minus sign of H2, so you will get H4. So H2, the general relation between Hadamard matrices of higher order is given over here, which is highlighted as a yellow color. So dear student, if you can see this one, so if I just multiply Hadamard matrices of n by n with the function, sine function of any Boolean function, then in that way I can also get the Gauss spectrum of any Boolean function. So this is one of the methods which will be utilized in our next lectures. Till that, I have to define some definition that strict avalanche criteria. So if I each output, I say the Boolean function, any Boolean function that satisfies SAC strict avalanche criteria, if each output bit changed with a probability of 0.5 whenever a single input bit is complemented. I mean to say whenever you just change single input in input, the corresponding output will be changed 50%. So this is the one of the definitions of a strict avalanche criteria. So if I can take this as a uh, another simplified definition with the help of directional derivative of any Boolean function f in the direction of a. It is like this one. So this is the directional derivative of a Boolean function, multi-valued Boolean function f in the direction of a. A Boolean function, a single-valued Boolean function satisfies that if f of x XOR f of x XOR a is balanced for every a belongs to vector space of a Boolean vectors with a is non-zero with Hamming weight is 1. So that is the at least minimum Hamming weight of this binary vector is 1. So if this is satisfied, and in that case we can say these Boolean functions satisfy the SAG criteria. Let us take one example. This is I take just what you call three Boolean function. This is f1, f2, f3, and f4. So these f1 take fundamentally three input, and f2 also take three input, and f2 also take uh, what you call it as a three input, and this is f3 is also taking three input. If you can see, the algebraic degree of f2 is 2. Here the algebraic degree of f1 is again 2 because of this term. And if you can see this one, the algebraic degree of f2 is again 2. So the algebraic degree of f3 is again 2 because of these terms. So I just take F1, F2, and this is F3. I calculate F1 XOR F2, then I calculate F1 XOR F2, then F2 XOR F3, then F1 XOR F2 XOR S3. So I just calculate this one. So if you can look over here, so these are, you know what, all are balanced Boolean functions. So if you can see here, number of zeros and number of ones are equal. Number of zeros and number of ones are equal. So in that way, I can say these are all balanced Boolean function. If I calculate this, what you call, if I can give you one example, like not like non-linearity, uh, if I can take one example, you know what, balanceness of all linear combination. I just take balance of all possible linear combination of f1, f2, and f3, and I have seen in this example that all these are balanced. So how I can calculate is what you call, if I have function like f2, f sorry, so I have like function f from z2 to z2. In that case, if I take 0, 0, if I take any function f from z2 to z2, that I take function like a table 0, 0, 0, 1, 1, 0, and 1, 1. The output of these are just my x, which is as a whole x, and x consists of four possibilities. So this is 0, 1, 1, and this is again 0. So this is my f of x, this is my x. So what I have to calculate is, I take one a like from this set, uh, because this is z22. So for sec I have to calculate this one. If you can see this one, so I have to calculate a. So I take a as 0, 1 with the Hamming weight is 1. So I have to calculate x XOR a. X XOR a means I have to add this number like 0 0 is XOR with 0 1. What I have to get, this is 0 1. So 0 0 0 1 XOR with 0 1. So what I have to get, 0 and 0. In that case, this will be 0 0. This is 0 0, sorry, this will be 0 1. So this will be again 1 1. This is again 1 and 0. In that case, if you can look over here, so I have this, calculate this one. So I have to apply F on this input. So F XOR with A. So what I have to get, if I apply F on 0 1. So what I have here, 0 and 1. When F is applied on 0 and 1, what I have get only 1. So if I apply 0 0 on F, 0 0, so when F is applied on 0 0 0 0, what is output? This one, 0. If I apply this, you know what, I have to apply these F on all these F XOR A output. So 1 1. When F was applied on 1 1, what will be its output? It is 0. So this is again 1 0. So what, when 1 0 is applied, I will get 1. So if you can see this one, so ultimately what I have to do is to calculate F of X XOR F of X XOR A. If I call it as a, so ultimately what I have to do is to, if you can see this one, this is 0 1 1 0, and this is again 1 0 0 1. So I have to omit this one just to uh, save my space. So if you can see 0 0 0 1 1 0 and 1 1. F of X was like 1 0, sorry, 0 1 1 and 0, and another one is F of X XOR with F of X XOR A. So uh, so let me elaborate this. 0 0 0 1 1 0 and 1 1. The F of X was 0 1 1 0. F of X XOR with A. What will be its output? 1 0 0 1. So I have to calculate X XOR F of X XOR A 4, checking whether this function F satisfies the set strict avalanche criteria or no. So I have to XOR all these. 0 XOR with 1, you will get 1. 1 XOR with 0, you will get 1. Then again 1, this is again 1. So if you can see this number of what we call number of zeros and number of ones are not equal in the output of this, what you call f of x XOR f of x XOR a. If you can look, go back into slides, this slide. So what does this definition mean? The function satisfies the stack if and only if this f of x XOR f of x XOR a is balanced. But in that case, if you can look over here, the number of zeros and number of ones are not same in that case. So the function f which I have taken over here is, it is not a balanced Boolean function. So this is my what you call the example to verify this stack of any Boolean function. Uh, I hope this lecture is quite interesting for you. Till then, Allah Hafiz, may Allah bless you all.